Okay, so let's see. Hopefully everybody can hear me. I see if the volume is up. It shouldn't have changed. Technology changed over break, so if nothing works, let me know. So yesterday was pretty exciting in here with nothing working, so and wires everywhere. So okay, we are going to start today on second one. Let him in. There we go. So we're going to start today on Unit 3. We're looking at the bones, the structure of the bones, the physiology of the bones. We're going to be looking at that. This is going to be a relatively short chapter, and no matter how hard I try to make it long. And then we're going to go on into muscles after this. Now, bear in mind that both this discussion on bones and the discussion on muscles is all about the physiology. It has nothing to do with the anatomy. In lab this afternoon, we'll be going over the skeletal muscles again. And I have some models for those of you that are on the ground to take a closer look at, have a little more time to examine them. As far as the lab test and the lecture test opened up. Actually, I accidentally opened it up yesterday instead of today for you. So since I didn't warn you, I've extended it till Saturday night at 11:59 instead of Friday night. You look stunned.
I thought it was Thursday.
Oh, no, it opens up today. It opened up yesterday and it's good till Saturday night, you know. So did you think it was going to open on Thursday? Did I tell you it was going to open on Thursday? I may.
Sure.
Yeah, I did.
I don't know.
I think so.
I saw it was open yesterday.
Well, I can. So it's okay. You know, if you were caught off guard, let me know. You know, if I said Thursday,
Saturday though, right? Like
it's right now. It's Saturday at 11:59 p.m. So if you need more time, let me know. Okay. So the lab test opens up Saturday and goes to the following Saturday. So the bone test opens up, you know, just because it opens on Saturday doesn't mean you have to take it Saturday. You've got a whole week to take the bone test. So want to get the lecture test done, and then we can go into the bone test because we've got more time to play with in lab than we do in lecture. We are tracking really well to get everything done on schedule. I hate having to rush at the end of the semester. So far we're tracking pretty good. So, will there be lecture in person on Thursday morning? No, because well, let's put it this way. If anybody shows up to take the test, there won't be a lecture in person. So I'll need to know ahead of time if anybody wants to take the test in person on Thursday, and it's perfectly fine to do that. I just need to know ahead of time so I can plan whether or not we're going to have a lecture. So anybody that, if nobody's coming in to take the test, then we'll go ahead and have class.
I won't this time. So.
Okay, you're not going to. You're going to take it online.
I'm gonna take it online too.
What about you? Okay, so let's plan on if no one's coming in to take the test on the ground, which is fine with me. I mean, you have that option. Then we'll just go ahead and plan on lecture on Thursday morning at the usual time, and that'll, you know, I'm even happier about that. So I better talk than give a test anyway. So okay. Okay, did that answer your question? I hope so. Okay, great, good. So this computer is slower than the old one too. doesn't respond as quickly. Yeah, so, okay, let's see what else. So lecture test will be open until Saturday night. If you have an issue, and I know that the internet's been really sketchy around the area lately, and I don't know why, you know, we've had all sorts of trouble here. We've had trouble in Morristown. We've had trouble at home. So for whatever reason. So if you have issues, it's not the end of the world, let me know. I can always fix that. So, because I don't know if it's the weather, I don't know if it's the Russians, I don't know what, you know, so anyway, okay. Any other questions? Then I'm going to open this up. This is what we used to call chapter 6. In fact, I think in some of the textbooks, they still call it chapter 6. Most anatomy textbooks are going to track with pretty much the same pattern. It doesn't matter what book you have. They tend to all track about the same pattern. And somewhere along chapter 6 or 7 is where the bones come in. So we're going to take a look at how bones function today. Now, it would be nice if our bones could respond to our muscles just like this, but we don't. But our bones are initially starting out as hyaline cartilage. We have a complete skeleton in place 6 weeks after conception. We're about a ½ an inch long, and we have a full skeleton of cartilage and membranes. Everything's there. All the structures that are going to become bones are there as cartilage. And starting about week 6, when we finished laying down the cartilage, we start converting that cartilage to bone. And that's a process that will take about 23 years to finish. So we don't really finish converting all the cartilage to bone until our very early 20s. The bone gives us great strength and support, and it functions to allow our muscles to do their job. Muscles aren't strong enough to do their job, to let us manipulate, as we say, manipulate our environment unless they can pull on a bone. The bone amplifies their strength. The bone works like a lever. Okay, so what do bones do? Well, obviously they support us. They hold up keep our organs in place. The organs in the thoracic cavity are held in place because the bones are there for the connective tissue to attach to. We protect these organs. You know, the ribs and the sternum protect the heart and lungs. The brain is protected by the skull. The spinal column protects the spinal cord. The viscera in the abdominal cavity are sort of on their own. But then when we get down into the pelvic cavity, we have protection from the pelvic girdle. We have a little protection for our ribs. Our ribs are high up here. They are under the diaphragm, but the ribs extend down far enough to give them a little bit of protection. Movement, we move our muscles contract, and they pull on bones. And by doing so, they increase their strength, and they can do things. Our bones are a tremendous source of calcium and phosphorus. Calcium is absolutely essential to making bones. So is phosphorus. But calcium is also used in skeletal muscle contraction. Without calcium, we can't contract our muscles. Without calcium, we can't generate nerve impulses. Without calcium, sperm cells can't penetrate an egg. So there's lots of things we use calcium for. And the greatest source of storing that is in our bones. We use our bones to make blood. There's a term here called hematopoiesis. It's a challenging word to say, even more challenging to spell it correctly. But this means blood cell generation. Now we have 7 different types of blood cells, 5 types of white cells, the red blood cells, and we have little cell fragments called the platelets. And in the middle of some of our bones, we make all these blood cells. So in what we call in the red marrow, that's a section in the center of certain bones. We also store fat. In the areas where we don't have red marrow, we have yellow marrow, and that's fat. And that is a stored energy source. As if we don't have enough fat stored in other places in our body, we can now store it in our bones. I don't think I've ever heard of anybody said that they had fatty bones, but it's, what can I say? And here's something that we talk more about now. Bones produce hormones. Hormones are chemical messengers. They tell our body to do things, like insulin tells the cells to allow sugar to come in. When there's more sugar in our blood, insulin, we've all heard of insulin. Insulin allows sugar to come into the cells and provide energy. And we regulate our blood sugar levels with insulin. Well, it turns out insulin isn't the only hormone out there. Osteocalcin helps to regulate insulin levels. And it isn't just osteocalcin. In AP2, you're going to hear about other hormones that are involved in insulin regulation and blood sugar levels. We regulate how much insulin can come out. We use osteocalcin to help this. We help maintain our glucose. The simple sugar is the #1 carbohydrate our bodies use for energy. And our metabolic activity, controlled by the bones. Who would have thunk that the bones are involved with all this? So now, just briefly, bones are found in 4 general shapes: the flat bones, the ribs, and the sternum, bones of the skull. A lot of these flat bones are the site of blood cell production. That's why we talk about them. The irregular bones, the hip bones, the pelvic girdle, the vertebrae. The pelvic girdle is also the site of a lot of blood cell production. The long bones, this hard-hitting definition, longer than they are wide. Very simplistic, but that's true. That means even a finger, a phalange, is a long bone. And support and movement, the ability to stand and sit, manipulate our environment, are mostly the long bones. And then the short bones fill in everything else. We have bones called sesamoid bones that look like sesame seeds. You ever notice that our kneecap, our patella, looks like a big sesame seed? So we have the little bones in our wrist and our ankle. These are the 4 different types. And you've all seen this already. So now when we look at bones, though, we're going to take a look at their structure. It isn't just what it is. It's not like, okay, this is a mandible. That's great. This is a mandible I'm holding up here. And you'll need to know that for your lab test. But let's take a look at what's underneath of this. So we can look at our bones by the makeup. Something that we all tend to forget about is that bones are living tissue. Even though it's 65% inorganic material made of calcium and phosphorus, it's 35% living because of the proteins in there, like collagen, by all the cells that are present, the bone cells, the osteocytes, the osteoblasts, the osteoclasts, and the bone stem cells. Plus, we have connective tissue and blood vessels and nerves running throughout the bone. So bones are living structures. Bone cells are living cells. Bones are living organs that are probably 60% non-living, but the other 40% is very much alive. I think we all tend to forget this because we look at a skeleton and say, well, this isn't alive. No, but the bone cells were at one time. Now, if we look at bones, we look at their structure in terms of gross anatomy, which is the overall anatomy. We look at them microscopically, both from the point of a cell and bone tissue, and we look at bones chemically. So gross anatomy, 2 terms here: Compact bone and spongy bone. Compact bone is the outer layer of every bone that we see. It's the hard, rigid layer of bone, like in this illustration here of the femur. It's been sliced in half. And the compact bone is the outer covering. You can see that the compact bone here. Oh, they took away my marker. Y'all should, yeah. I just realized I don't have, they took my marker when they put this up. Well, I guess you should be happy. You won't see any more scribbles on the screen anymore. That's not nice. So
yeah, they changed your monitor.
they changed, yeah, the old monitor's laying over here, the one that had everything connected to it. We had to put a USB extender out here, a hub, to make everything else fit. Okay, so no more drawing on the board, on the screen. The compact bone is the outer covering. It is hard, it is dense. It makes the bone surface smooth. It has points of attachment for muscles on them. Underneath the compact bone, at the ends of the long bones, for example, we have what's known as spongy bone. Spongy bone looks like a sponge. It has little tiny flat structures in here called trabeculae. And spongy bone is just as strong as the compact bone. The compact bone gets its strength by being very dense and you know, a hard surface to try and, you know, it supports itself because it's very rigid. It's like layers of concrete. But the spongy bone works by these trabeculae are designed to function like shock absorbers and spread the shock of motion out. So what they don't have in mass for strength, they have in many individual, many trabeculae that work together to spread out the forces that they're dealing with. So spongy bone is usually, so the two types of bone that we encounter are compact bone and spongy bone. In this case, we see spongy bone at the head of the femur and the neck of the femur. And I'll just digress here for a second. That's a really good thing because the head of the femur and the neck of the femur is where we deal with a lot of stresses. The stress of moving, running, climbing, walking upstairs, walking downstairs, riding a bicycle, any kind of motion that involves your legs is going to be, the stresses are going to come up and be applied to the neck and to the head of the femur. And then it's transferred into the pelvic girdle and up the spinal column. But because the bone, the head of the femur, the neck of the femur is a layer of compact bone and a overlaying spongy bone, that area deals with the stresses very, very easily. And if we lose the spongy bone underneath the compact bone, then that becomes the #1 location for hip fractures, is right at the neck of the femur. We'll get into that a little later on. Okay. Flat bones, irregular bones, short bones, the reason we mentioned those earlier is because they consist of they're made up with a layer of spongy bone surrounded by two layers of compact bone. And we call this DIPLOE. It's like a sandwich. And here you have a layer of the spongy bone with the hard layer, the compact bone on either side of this. Now, another term, periosteum, is a membrane that covers the outside of the compact bone. So whatever kind of bone you have, you're going to have a layer called periosteum on the outer surface of it. Underneath the compact bone, before you get to the spongy bone, you have endosteum. So let's show you what this looks like. This is DIPLOE. You have compact bone on both sides, This is a bone, one of the bones of the skull. It looks like it's a parietal bone. And you can see it has three layers. It has a layer of compact bone on its surface, a layer of spongy bone in between, and then another layer of compact bone inside the cranial cavity where the brain would be located. We have this ideal arrangement here because the bones of the skull are lightweight. It's not solid bone. It's not solid compact bone. It's a lightweight structure designed to absorb shock. These trabeculae that you see at the bottom of the picture here, these little, spines and ridges and grooves, they take any kind of shock of motion and spread it out so that it doesn't cause any kind of damage. The shock of turning your head is spread out through the spongy bone in here. Bumping your head, for example, on something is spread out. And any kind of action like that, wherever we have spongy bone, we're going to spread it out. So the force that's applied to a bone at a location like that just spreads out. So this diploe is everywhere we want to have great strength without a lot of weight. Because if we didn't have this diploe, imagine how thick our skulls would have to be to protect us. Can you imagine that our skull would be as thick as the femur, for example, largest bone in our body? It would be 3 or 4 times thicker than it is now, and it would be, we'd have to have these massive neck muscles to hold our heads up. And here's another drawing of the diploe, what it looks like. That periosteum layer is on the outside of all bones, whether it is a spongy bone, like a rib. This is a skull bone, but it could be a rib. It could be the sternum. They're all built like this. And they all have this layer of membrane called the periosteum. If you've ever eaten ribs, and you're gnawing on that rib because all the meat's gone, but there's still a little bit of tissue left because you really enjoyed your ribs and you're just sort of chewing on it a little bit. You're probably chewing on the periosteum. So I hope that didn't ruin ribs for anybody. So I don't like the look you're giving me on that. So no, but that's, it's no big deal. And we've all done that. If you like to eat ribs of any kind, and you're just sort of chewing on it and you see this really thin membrane that comes off, that's just part of the rib. That's the covering of the bone. It's just connective tissue. So anyway. So that we all of our bones have a layer of periosteum. What's the periosteum do? Well, the periosteum, among other things, holds blood vessels and nerves to the bone. Because remember, the bone is living tissue. And bones, and these long bones in particular, they're full of foramens that we didn't see when we looked at our models. We looked at lots and lots of foramens on all the bones. I mean, like the skull is chock full of foramens. Okay, so are the long bones. Blood vessels go in through foramens in the long bones. They're held onto the bone by the periosteum. So we're going to look at a long bone. The long bone, the shaft of the long bone is called the diaphysis. So, and I only introduced diaphysis because I want to talk about the epiphysis here. Diaphysis is the shaft of the long bone. And the shaft of the long bone will have an epiphysis at both the proximal and distal end, top and bottom. And the reason I mentioned the epiphysis is because that's where bone growth takes place. So the diaphysis is the shaft that gives us the long bone. It has a central cavity called the medullary cavity. And that's where we have our bone marrow. The bone marrow is found usually in the middle, in this cavity in the middle of our long bones. Now, as adults, most of our long bones are filled with yellow marrow, fat. But some places we still have the red marrow. Now, when we were kids, every bone was filled up with red marrow. We were busy making lots and lots of blood cells all the time. But as we get older, we put more yellow marrow, more fat into the medullary cavities to use that for energy storage. We still have areas where we have to make blood. We have to make the sternum, probably the #1 area for producing blood cells. Yeah. You ever had an X-ray and they have a lead apron, they put it on you, they cover your chest. It usually covers your chest and the inguinal region. So you're protecting your gamete production, but you're also protecting the sternum. That's probably the #1 area now where we make blood cells. If you've ever heard knew anybody that needed a stem cell transplant, for example, the testing usually takes place in the iliac crest, because the iliac crest is another center of blood cell production. And see, blood cells all come from one stem cell. One stem cell produces all 7 types of the 5 white ones and the red ones and platelets. And for whatever reason, it's easier to get samples at the iliac crest. So that's another area where we have red marrow. So there aren't many places that we have that anymore, but enough to keep our blood supply going on. Now, the epiphyses is where the bones grow. You know, we started out as a hyaline cartilage skeleton, and that was great. But at week 6 after conception, at week 6, we start calcifying, ossifying that bone, that cartilage, and converting it into bone. And that process takes another 23 years. The growth that occurs in our long bones takes place in these structures called the epiphyses. This is an area where while we ossify most of our bone, most of our long bones, we turn them into real bone. We keep an area at each end of the long bones called the epiphyses. And there we keep hyaline cartilage growing until we're about 23 years old. We keep making cartilage. The bone keeps growing longer. Lengthwise growth of our bones takes place at both ends. The bones grow outward from the ends. And so when we go through puberty, for example, we have our growth spurts. We're growing from the ends of the long bones. And all long bones have these growth plates. We call it the epiphyseal plate or growth plate. And when we look at under an X-ray here in a second, you're going to see where the hyaline cartilage is because it's a dark line. It's a gap because hyaline cartilage is soft tissue. Soft tissue doesn't show up in X-ray. This is, let me just jump ahead here. This is what the growth plate looks like. This is the epiphyseal plate right here. This dark area is not a fracture in the bone. It is showing the presence of hyaline cartilage. Soft tissue doesn't show up on X-ray. It shows up as a black line. And so if we're looking at this illustration here, this X-ray, you can see on the tibia and to some extent, and also on the fibula over here, you can see the dark line there because growth is still going on in the tibia and in the fibula. Now, if we look at the femur, we can see that the growth plate is just about done. You know, there's still some shadow in there, but it's also closing. So the growth plate is on the femur is starting to turn into not an epiphyseal plate, but an epiphyseal line. And the line is the scar of the growing areas. And so it'll look like this. You can see this is a child of, I don't know what age they have here, but you can definitely see the plates here on the tibia and on the fibula and also on the femur. But over here as an adult, now all we have is the epiphyseal line, this white line across here where the plates have closed. And so if you have an X-ray of an individual and you can't communicate or they're of an indeterminate age, and for whatever reason you don't know anything, perhaps you're examining a a body. You know, you're X-raying the body, trying to determine information about it. And you can say, well, you know, you can make an estimate of the age of the individual based on what you see in the bones, because early 20s is a pretty good time frame for when those plates close. Now, let me go back and pick this up. Now, where are they located on the bone? Well, the epiphyses are at either end of the bone, the proximal or top and distal in the end. So here we see on a femur that the epiphyses are up here. We call it the proximal epiphysis. And there's our growth plate right there. In this case, it's a line because it's closed. And there's one down here you can't see because they didn't draw it that way. But the diaphysis, the shaft, runs from here to here, and the epiphyses are at either end. Now, in this case, with our long bone, you can see that there's compact bone on the outside at the epiphysis and spongy bone underneath. And the same applies down at the distal end. The compact bone is very thick in the shaft itself on the diaphysis. So we have great strength. We have great resistance to compression. We have great resistance to twisting here in the long bone. And at the ends of the bone, where we have the compact bone, we have great resistance to shock. We have the ability to manipulate and manage shock as we move. Okay. So we're looking at a section of a humerus. Here, you would see the compact bone. You know, this is the vertical structure of the bone that runs up and down on the shaft. This blue band out here is the periosteum. Here we have the endosteum. You know, so the periosteum lines the compact bone. The endosteum starts lining the end of the compact bone, but it also continues to line the spongy bone too. But notice that the spongy bone is irregular in shape. It doesn't have this nice uniform pattern like the compact bone does. And it's not supposed to. It's supposed to be irregular so that forces that are applied to this bone can be spread out. Because no matter how strong a force is, if you allow it to spread out, it gets weaker and weaker. Imagine if we opened up, I don't even know if there is one on campus, but if there was a fire hydrant out here in front of the building, and imagine if we were able to get access to the wrench they use to open that, you know. And so I'm going to open this, and you're looking for extra credit, and you volunteered to stand directly in front of the hydrant when the cap comes off. Okay. Hey, it's worth 5 points. Okay. You know.
I'll take it.
Yeah. And that's okay. So I don't have a wrench, so you're out of luck. So, but imagine what would happen if I unfastened that and turned the water on. It would probably knock you over. You're standing right in front of it. But what if you're standing 20 feet away? Is it going to do anything to you? No, because by the time the water column has gotten 20 feet out there, it's already hit the ground and spreading out. The worst you're going to get is you're going to get your feet wet. You don't get extra credit for wet feet.
Or a slip.
Or you slip, yeah. So, because the force has spread out. And that's what, you know, in sort of a example, that's what spongy bone does. It allows forces that are applied to them to spread out. And so they don't hurt. They don't bother us. They don't do anything to us. We get used to it. So walking upstairs doesn't hurt. Now imagine what happens to our femur if all that spongy bone disappears. And all you have left is the outer shell of the compact bone. The compact bone is very strong. But if there's nothing underneath the compact, but the compact bone has to work with the spongy bone. And imagine if there's nothing there underneath the compact bone, and the spongy bone is gone. What happens then? The bone snaps. You know, when grandma trips on a throw rug, I always wonder why they call them throw rugs. When grandma trips on the throw rug and falls down, or sneezes really hard and her femur snaps at the neck. How come it snapped? Because there's nothing underneath the compact bone to prevent that. The shock of the sneeze, the shock of coughing, the shock of rolling over in bed at night or tripping on a rug, all that is normally absorbed by the spongy bone. But if the spongy bone is gone, then the neck of the femur snaps. And that's how people break their hips. That's what a hip fracture is, breaking the neck of the femur. Now, who ends up without spongy bone? People with osteoporosis. Because osteoporosis, and I'm getting way ahead, but I'll just come back to it. Back to where I was. Osteoporosis dissolves away all that spongy bone at the diaphyses. And that's why hip fractures are so common in a lot of elderly patients, mostly elderly females. You know, because your postmenopausal female isn't producing estrogen, and estrogen is essential for bone growth and development. So now I'll just leave that out there for now. Okay, so I mentioned the periosteum. You've all probably experienced the periosteum if you've ever eaten ribs. It is a connective tissue layer. It has two parts to it. It has an outer layer that made up of what are known as Sharpie's fibers, which is a lot like Velcro. You know, the hook portion of Velcro, and that's what holds the blood vessels in place. There are what we call nutrient foramens in the long bones, and they're held there by the Sharpie's fibers. Underneath this is a second layer called the osteogenic layer. Now, I've said several times that whenever you have the suffix genesis or genic, it means creation. Osteogenic means bone creation layer. This is where the bone stem cells are located, the osteogenic stem cells that are going to give you all of the bone cells you need. You have a layer here underneath the periosteum. You have a layer of osteogenic cells underneath the endosteum. And these stem cells are going to become all four of the different types of bone cells. And so, and I mentioned the nutrient foramen now. So this is what our periosteum looks like. You know, you see the Sharpie's fibers, and you know, sort of just imagine Velcro. There is the artery coming into the bone through the nutrient foramen, held in place by the Sharpie's fibers, and that will penetrate and go in through all these various cavities in the bone. The endosteum is the inner layer of the compact bone. The periosteum is the outer layer of it. And both the endosteum and the periosteum are going to have an osteogenic layer there. So, okay. The endosteum covers the inner bone surface. It covers the trabeculae. Any canal, any nutrient foramen that leads to a canal, and we have lots and lots of little canals throughout our bone, is covered with endosteum. And this is also where we can make bone cells. The four different types of bone cells come from the endosteum and the periosteum. So within the long bone, we have the trabeculae. In the spongy bone, we also have the medullary cavity. We find that red marrow is usually present in the spongy bone. remember that spongy bones can be found in the diaphyses at the ends of the long bones. That's where you're going to find the red marrow. That's why, like, the head of the femur can make blood cells. The head of the tibia can make blood cells. The head of the humerus can make blood cells because the spongy bone there has red bone marrow in and around the trabeculae. We all have red bone marrow in our bodies. The sternum, the ribs, the flat bones of the skull, the head of the humerus, the head of the femur, the iliac crest, for example. That's where that's where all of our blood cell production is taking place. We used to be all red marrow as children. Now most of our marrow is yellow marrow. But if a person develops anemia, anemia is a symptom. Anemia is not a disease. Anemia is a symptom of a condition. Anemia means that you are deficient in delivering oxygen to your cells. It's essentially what anemia means. Anemia is the symptom showing up here. A person that has anemia, is experiencing anemia, may have a low red cell count, for example, or they may have a low iron count. Now, what is causing that anemia? Then you treat the anemia, you treat the symptoms, but you got to find out what the cause is. So anemia itself is not a disease; it is a symptom of something. But if a person does become anemic, then we will often revert, and as an adult, we will often revert the yellow marrow back to red marrow to try and make more blood cells that they need. The problem with that is that even if we do that, if there's a problem in making red blood cells, for example, all we're going to do is if there's a problem and we're making defective red cells with the existing red bone marrow, if we up the production, are we still going to be making more defective red cells or defective white cells? So yes, we can convert yellow to red and make more blood, but is that going to solve the problem? Our bodies are very good at following the statement, if some is good, more is better. But that usually isn't true. That's usually not a good thing. Our bodies will compensate for problems by, hey, I'll just make some more let's say we don't have any iodine in our diet to make thyroid hormone. And so our thyroid isn't functioning properly. So what will happen is the brain will say, well, let's make some more hormone that stimulates the thyroid. Then we'll make more thyroid hormone. Well, if the problem is, you can't make thyroid hormone without iodine. If you're not getting any iodine, you can have all what we call thyroid stimulating hormone that you want. It's not going to help. Our bodies like to enlarge things when things stop working. Enlarged hearts. A person with heart disease, their heart will get bigger to try and compensate for a problem in pumping. But an enlarged heart is a symptom of heart disease occurring here. An enlarged heart is less efficient. The bigger the heart gets, the harder it has to work to try and pump blood. An enlarged heart can often be massive. Your typical heart is this is life size. So it's about the size of your fist, So your heart's about this big. People with an enlarged heart can have a heart the size of a football, and it is much less efficient than one that's the size of your fist. Okay, I digress. There's the bone marrow. Red bone marrow in the trabeculae of the spongy bone is going to be where we're making our blood cells. The yellow marrow is fat. You can see it in there. And that's our sources of energy, stored energy in there. And, in some societies, eating a cooked bone a long bone like that, eating the marrow out of it is considered a delicacy. So just throwing it out there for you. So this is what it looks like. This is the head of the femur with the, opened up, and we can see what the red marrow looks like. We can see that, you can see the spongy bone, and you can see all, all that is, that red area is hematopoietic tissue. I almost got it out right. So, and this is where we make blood cells, but there's still yellow marrow inside there for energy too. It's okay. So anyway, now, okay. Now, microscopically, continuing on here, taking a look at these individual cells, there are 4 types of cells that we encounter in bone. 4 living cells. We have what are known as the osteogenic cells, and they are the stem cells. We have the osteoblasts. Osteoblasts are the bone builders. Anytime you have the suffix blast on any kind of cell, it's a builder. Osteoblast, chondroblast, fibroblast, they're going to make those kind of cells. Cartilage is made from chondroblasts, for example. Osteoblasts lay down the matrix for bone cells, and then they get trapped in the matrix and become osteocytes, which are the living bone cells. The osteoclasts are a little different. Osteoclasts are huge bone cells that are packed full of lysosomes that slide across the surface of bone and use those digestive enzymes in the lysosomes to dissolve the bone to get the calcium out. So it's like those huge road grading machines that drive along, they bring it along over asphalt, and it just chops up the asphalt as it goes along, and you have a new road surface underneath. So maybe they'll get around to putting our new road surface down out there. That I digress. So the osteoclasts are the bone breakers, if you will. Now, everything is derived from the osteogenic cells. The osteogenic cells are the stem cells. Now, like any good stem cell, it follows a pattern. Osteogenic cells can differentiate into any of the other 3 types. But to make certain that we always have enough stem cells, when the osteogenic cell divides, it will always divide, it'll divide through mitosis. And osteogenic mitosis, type A, type B. No difference between A and B, except the B cells are going to go off and become osteocytes, osteoblasts, osteoclasts. And type A stay as the osteogenic cells. So we can do it all over again. So stem cells will always copy themselves first, so they can divide into, so half of them can divide into the other types of cells. Let me see if I can show this on the screen like I wanted to. Hopefully this is not showing up backwards. Yeah, when you see it. If it is, we got more problems with the computer. But osteogenic cells are what we have in the periosteum. They undergo mitosis, and they give you 2 types of osteogenic daughter cells. Half of them stay as osteogenic cells to keep doing it again, and the other half become the osteoblasts, the osteocytes, and the osteoclasts. So, okay, let's hope that worked better than it looked there. So any good stem cell is always going to do that. you'll see that when we get into AP2, you'll see how the stem cells in the testes and the stem cells in the ovaries produce gametes. Same way. We have we have spermatogenic stem cells in the testes that produce sperm cells. And the first thing they do is undergo mitosis. So half of them can continue to produce sperm cells, and the other half go off and become sperm cells. So any good stem cell is always going to maintain its own population there. So the osteogenic cells are going to give rise to the other three types and additional osteogenic cells. Osteoblasts, the bone building cells, the bone forming cells, they lay down the matrix that will eventually harden to give us the calcium and phosphorus salts to give us the hard bone. The osteoclasts are going to be the bone dissolvers, and the osteocytes are the living bone cells trapped in lacunae, but communicating to each other. So now, this is what an osteoclast looks like. It has there's like a brushed edge to it, and it just sort of grinds along over the bone and dissolves the bone to get the calcium out. So the calcium can be used to make new bone, because we're always remodeling our bone. We're always rebuilding our skeleton. We're responding to stresses all the time. We shape our bones, we rebuild our bones. We have a completely new skeleton of compact bone in place every 10 years. We replace our spongy bone every 2 or 3 years, and we're doing it with these osteoclasts. We don't lose the calcium. We use it to make other bone. Now, when your patient is a postmenopausal female, I haven't thrown her under the bus for a while, but I'll do it today. The postmenopausal female, she's no longer producing estrogen. If she didn't have a lot of calcium or enough calcium in her diet prior to menopause, if she didn't have enough exercise prior to menopause, she will eventually start experiencing bone loss through osteoporosis. And that is because there's no more estrogen. The ovaries shut down. The ovaries produce estrogen. That's the female sex hormone. Estrogen stimulates bone growth and deposition, calcium deposition. Without the estrogen, you're not going to make a lot of new bone. Now, if she's maintained good levels of calcium in her diet her whole life, and she's exercised a lot, then she's not, and she continues to eat foods rich in calcium now, she's probably not going to have a lot of issues. But if she hasn't, then she's probably going to develop osteoporosis. And osteoporosis is just where bone breakdown occurs faster than bone buildup. That's all it is. So, why is it confined mostly to, mostly, not completely, mostly to females? Because males produce testosterone until the day they die. So they don't shut down their testosterone production. Males don't go through any kind of menopausal activity like that. And so they will continue to produce testosterone, and they're not going to see an absence in bone breakdown. Now, can males develop osteoporosis? Yes, of course they can, but it's very, very rare. Well, not sure. It's unusual, but it can happen. Okay. Now, the structure of our long bones, there's a term for it here. We call it, on the compact bone, we call it lamellar bone. A lamella is a layer. A cross section of a compact bone specimen looks like the rings in a tree trunk. If you cut a tree down and you look at the stump, you can see the rings in the tree, and you can determine the age of the tree and all sorts of stuff that botany types can do. These layers of bone will also give us a story. These lamella these rings of bone will also give us a story about the bone. So when we look at lamellar bone, we have three things that we see right away. First of all, we have what are called osteons. And osteons are like columns or pillars that run the length of a long bone. A pillar of bone, an osteon is a pillar of bone that runs from one end of the bone to the other. So it isn't like it's partway through here. It is a circular pillar. Imagine if this were a bone, if these three markers were a bone, each one of these markers would be an osteon. It would represent a column of bone that comes up through the entire shaft of the bone. So, within these osteons, we have canals. We have canals all over the place. We have tiny canals called canaliculi that run through here. So that every cell, every osteocyte can talk to every other osteocyte. Every osteocyte can run an extension of its cytoplasm through a tiny canal to another osteocyte. And so they can communicate, they can share nutrients and get rid of waste products. They know when they've been stressed. They know when there are demands being placed on the bone to do things. Let's say that you decide you want to be an Olympic weightlifter, okay? And so you start lifting weights and working out every day. And pretty soon you can lift 1,000 pounds over your head, okay? Your bones are going to change. Your bones are going to get stronger in response to your muscles getting stronger. Your bones are going to get bigger. How do they know to get bigger? The living cells inside the bone can detect the new stresses placed on them, and they can respond by saying, we need to build up more bone. We need more osteocytes in here. And so your bone will get thicker and stronger. And so they respond to that. Or, yes?
So, like, if you were to work out as your bones get bigger and stronger, does that mean that they're least likely to break?
Well, they're going to get less, they're going to be more powerful. They're going to respond to the demands the muscles makes in them. So they should be less, they're not as fragile. They're not as thin. So, because a thin bone, while is strong, is more prone to breakage. Remember the fibula. Fibula is there on the outside of our lower leg, doing absolutely nothing for us. Most injuries in the wintertime from skiing, the classic broken leg is the fibula, because it sits, first of all, it sits out there on the edge of the leg, doesn't do anything, it's not protected, and it's a weak little bone, and it breaks easy. You got to work hard. You got to work really hard to break your tibia or your femur, but the fibula is easy to break. So now let's say, I'm going to take your question one step further, that you're an astronaut now, and you're in the space station, and you're going for the endurance record of like a year or something or whatever. You don't have any gravity in the space station. You exercise every day on resistance equipment. That's probably where Bowflex and that kind of stuff was developed from the space, space travel. But gravity's not our friend. It pulls down on us all the time. We are constantly fighting that. You take that away, and a lot of the work that our bones have to do is gone. A year and a half after you went into space, you come back and try and walk, and you can't walk. Your muscles have shrunk, and your bones have resculpted themselves, so they're very, very fragile. And so if you ever see any video of people coming back from long duration space flights, they usually carried out of the landing vehicle, because if they tried to stand up, their bones would snap. Now they recover very quickly after that. It doesn't take long for the bones to get back to normal, but the bones have reshaped themselves because of a lack of stress. They have reshaped themselves to where they become thinner and thinner. The muscle cells have gotten smaller. Now we don't grow new cells. When we exercise, our muscle cells either get bigger because of the demands placed on them, or they shrink because of a lack of demand, but we don't lose the cells. And so, yeah.
Do you think people who like do the long duration space trips, whenever, do you think they have to go through physical therapy when they get back?
Oh, I'm sure they do. Because a lot of them, they can't walk well. There was a couple of years ago, there were twin brothers, astronauts. They were the Kelly brothers. They'd both been in space, but the one brother went in space to, for a long duration, for a year. And they were comparing his brother on Earth to the one in space. And when he came back, the one from the space station was like 6 inches taller, because his bones, the cartilage had spread out more, and he shrank back to his normal height. You don't want to have your twin brother to be 6 inches taller than you, So, but there was a lot of physical therapy they had to undergo to get to where they could start walking again. They knew how to walk, but for a year they've been floating in the space station. So, I would imagine the first time you get up in the middle of the night to go to the bathroom, like, I can't float, that's a real shocker. But yeah, there's a lot of therapy involved to get them back to normal. And I have read that a lot of people from long duration don't completely recover their muscle strength or their bone strength after that. So, because the only kind of exercise you can do in space is with resistance equipment, pulling in, like a Bowflex or something like that. Lifting weights is, hey, I'm doing 1,000 pounds. Hey, this is great, with your finger. It doesn't help. So, okay. So all these canals allow the living cells to talk to other living cells. They know when to build up bone and when to tear down bone based on the stresses or the lack of stresses being applied to that bone. Now, we also have to fill in, because when if I use this example of the markers as a long bone, you'll notice that the markers are there's not a nice round surface around the bone. So we have fill-in lamellae. We have lamellae that surrounds the bone to make it smooth. We have lamellae that fill in the areas around these osteons. Now, this is what I'm talking about. This round column up here at the top, labeled osteon, is the osteon. It's a column that runs the entire length of the long bone. And it's made of rings of bone. And the rings of bone are called the lamellae. They're laid down. As these osteons grow, the lamellae lay down. We trap more living bone cells inside here. The little dark spots here are the lacunae in here, and the living cells are inside the lacunae, like down here. Each one of these little cavities is a lacunae, and each one of the cells inside is an osteocyte. Now, they have projections of their cytoplasm. Their cell membrane sticks out through these canals. There's these tiny the canaliculus or canaliculi, so that this cell can communicate to that one, and that one can communicate to the one that's up here and down here, and they talk back and forth. So all these living cells are in contact with each other, and that means that what's happening up here on the top of the osteon is also the cells down here are aware of it way down here. It's like these cells here, yes, they're not adjacent to the ones up here, but they know what's happening because everybody is communicating on each layer. Each ring is called a lamella. And the lamellas are what give our bones, the compact bone, the strength. The lamella is made of the matrix, the hard matrix of calcium and phosphorus salts, but it's also wrapped by a layer of collagen fibers. So each one of these rings is like concrete and rebar put in here. Now, where do all the nutrients come from? Well, here's our bone right here, and we have blood vessels that have penetrated through the bone through these nutrient foramens. We have arteries and veins and nervous tissue, And you'll notice that within the bone, there are perforating canals that connect to each one of these osteons. And then the arteries and veins can break, the arteries can break down into capillaries and supply nutrients to every one of these living cells. So we have arteries and veins, and the nervous tissue then communicates and tells the brain, hey, you know, we need more bone growth going on here. So we have, you know, all of these cells, they don't operate in a vacuum. They don't operate, they're not isolated. They're not trapped in, well, they can't move in a sense, but they are definitely not isolated. They're communicating with each other. Yeah, so this is what the osteon looks like. The osteon is just the column, the cylinder of bone made out of the various rings, the lamellae. And every time a new ring is laid down, the ring is wrapped in collagen fibers, and the collagen fibers run in the opposite direction than the layer underneath it. So you get a crosshatch effect, which makes it stronger, makes it much stronger in here. And then of course we have the salts, the calcium and phosphorus salts embedded among the collagen fibers. But by having the collagen fibers wrapped around here in opposite directions, it's very hard to damage this bone by twisting it. Because we've all taken a step and turned our leg and didn't snap our leg. You know, sometimes we do. You know, sometimes we, you know, a lot of times in Friday night football on a rainy night, and you get a player that puts their foot down and they turn to make their cut, and their leg turned, but their foot didn't go with it, and it snaps, the bone snaps, the fibula snaps. You know, but usually, you know, all the stresses that we do, the different movements we make, we don't hurt our bone. The strength of the collagen fibers wrapped around the osteon gives us this incredible strength here that you know, we just don't snap our bones. Because if you've ever had a fracture, you know that it takes a lot of effort to break your bone. Usually, if you've ever had one, the first thing is like, oh, it's broken, you know. Because we never remember the point where the bone broke. We know it's broken. We know what happened, you know, but we never actually remember it breaking. But I know I've always been surprised. Oh, it's broken, you know, because it does take a lot of energy, a lot of force applied in the right location at the right time to cause it to break. Okay, so the central canal. The canal that runs through the osteon is called the central canal or the Havursian canal. That's where we get our blood vessels and our nerves. Then we have penetrating canals or Volkmann's canals that go off to the side that supply blood to all the other, eventually to all the cells. The lacunae, you know, your osteoblast is laying down matrix and it sort of builds itself into a corner. And the matrix hardens up, and now the osteoblast has become an osteocyte. But it left canals as it's laying down its matrix. The canals, the caniculi, are going to allow each lacunae to connect to every other lacunae, and also to the canal in the middle. Let me see if I got so let me go back. Well, this will work. Here's the central canal of an osteon. This is an osteon right here. You know, these are lamella here. They're the osteocytes. The canaliculi, the canals, all connect to each other and connect to the Havursian canal, the central canal of each osteon. So we go back here. Yeah, so there's your central canal right there in the middle. And all these little tiny canals that you see down here, they're all connecting to this central canal where the blood vessels and nerves are located. Okay. So the osteocytes live within the lacunae. They have their cytoplasmic extensions that connect through the canals to other osteocytes. They have gap junctions that connect remember those are the ones with like little holes there. And they connect with the gap junctions, cell to cell, and ultimately to the central canal. So they can pass nutrients back and forth, and waste back and forth, and information back and forth. So now the interstitial and circumferential lamellae, the interstitial lamellae are just to fill in. That's what this stuff is, like here in the edges where we have lots of layers of compact bone. It doesn't seem to fit the pattern of a full-blown column. Maybe this was an osteon that was remodeled and had gotten cut up during the remodeling process. And then the circumferential lamellae is the rings of bone that go all the way around the whole bone, just to give you a nice smooth surface, but also to help make sure that while the osteons resist twisting, the whole bone can resist twisting thanks to these around this lamellae around the whole shaft. This is what it looks like. There's an osteon right there. There's another osteon. The interstitial lamellae is at areas in between the osteons, and then the circumferential lamellae would be out around on the ring. Now the osteon looks very organized. It's the OCD of bone. Okay, everything is done just right. Spongy bone doesn't look like it's organized, but it is. Spongy bone has these trabeculae. The trabeculae line up along the pattern of stress. The stresses that a bone the stresses that are applied to the bone cause the trabeculae to form in that area. So the more stress that is placed there on a bone, the more trabeculae in the spongy bone you're going to get in that region. And what it does is again, it's like the fire hydrant. It spreads out. The shock is spread out, so you don't feel the shock. You don't feel the shock in your hip of walking up a flight of stairs, or running, or riding a bicycle, or swimming, or any kind of physical activity. You don't feel the shock because the shock is spread out. It is dissipated through all the trabeculae. Because we don't want to feel that shock. We want to be able to do things. So our trabeculae gives our spongy bone a great deal of strength without a lot of weight. Because you imagine how much larger the muscles would have to be to move us if we had no spongy bone, if we had to depend totally on compact bone. Okay. And of course, there's our spongy bone again, the DIPLOE, with a compact bone, spongy bone, compact bone, and again, the trabeculae here. Now our bone, as I said, is living tissue, but it's only about 40% living. It's only about 40% organic. And it means the cells, the osteogenic cells, the osteoblasts, the osteocytes, bone lining cells are the osteoblast cells. They line all the cavities. But so we have the matrix, that's the osteoid, and all the living cells. We have the proteins, we have the collagen fibers, we have the connective tissue. All this is organic material. Now the living cells are just, collagen's not alive, protein's not alive, but the cells are alive. So about 30% or 33% or whatever of the bone, of our bone, is living material or organic material, including the living cells. The rest of it is salts, calcium and phosphorus salts. It is calcium, phosphorus, and surrounded by collagen fibers. Collagen fibers have this unique property known as sacrificial bonds. Collagen fibers will break when they are exposed to trauma. It takes a lot of energy to break the bonds of the collagen fiber molecules. Because, you know, we've always said they're as strong as steel, you know, the same size. And so they're very, very strong. What happens is that the collagen fibers will absorb energy. And if the bond breaks, it takes a great deal of energy to break that bond. That energy then can't be used to damage the bone itself. So the collagen fibers will snap in lieu of the bone. And then the collagen fibers will regenerate and everything will be fine. So the collagen fibers absorb the blow. So in addition to the trabeculae and the spongy bone, the collagen fibers function by absorbing the energy that would be used, that would normally cause trauma, by allowing themselves to get broken. So, and so the bond, but then the bond will just reform among the collagen fibers, because we do things to ourselves all the time, and we have no lasting effect. You know, we fall down when we're kids. We fall down a lot. We run into things. You know, as we get older, we still fall down and we have accidents. But you know, usually we recover from that. And, you know, you may be bruised and cut, but you don't have any fractures or anything like that. So thanks to the collagen fibers and the sacrificial bonds. Now, most of our bone is made up of calcium and phosphorus. Bone, I like this, is half as strong as steel in resisting compression. You can't squeeze it and crunch it by pressing against it. And it is as strong as steel in resisting tension. It takes a lot to bend a bone. It takes a great deal of effort to get a bone to fracture. And bones last a long time, long after the organic material of an individual has decomposed, the bones are left behind. Skeletons are found all the time, from the Civil War 150 years ago, from the Revolutionary War, 250 years ago, something like that. We're finding whenever there's any kind of construction, there's always a surprise when someone discovers a cemetery somewhere. And the bones are still there. The bodies have decayed, but the bones are still there. And the bones can still tell you a lot about the individual. You can determine their nutrition. You can determine their age. Because, you know, if the bones didn't grow very well, they probably had poor nutrition. You might be able to figure out the cause of death. You know, a skull with a great big hole in the side of it might be an indicator that that was the cause of death, or not. You got to be careful on stuff like that. You can, if a person was poisoned, even 100 years later, many of the poisons will still be found embedded in the bone crystal. You know, it was thought that Napoleon, if you know your European history, Napoleon went into exile on an island off the coast of South America, and he died within a few years of going into exile. And it was thought that his staff poisoned him because they couldn't bear the thought, well, he's not the emperor of France anymore, so let's just kill him because he's suffering. So we'll just kill him. And supposedly they poisoned him with arsenic. Arsenic stays in bones for a long time. And I think I read somewhere that there is evidence that they did that. But certain types of poisons will stay in bone for hundreds of years. So anyway, on that cheery note, I think I'll call it a day. Get to a different camera. So, yeah. So they gave me a brand new camera too that is sort of strange. I can do this with it. Yeah, there we go. How about that? Yeah, you know. Anyway, since everybody seems to want to take the test online, which is fine with me, let's plan on having a lecture then on Thursday. We'll continue on with our bones. I didn't get quite as far as I wanted to. I led myself down too many rabbit holes today. So, but if anybody has any questions, be sure to shoot me an email and I will get back to you. And lab this afternoon, we are going to look at the muscles again. So, and I'll get us out of here. If this is going to work. Don't you love technology? There we go.